so if you don't mind, if you could check to see that the people are in the meeting that we're calling up. Bjorn, for instance, he's the first one up and he's supposed to be here. Oh yeah, he's there. Well, some people are good enough. Yeah, that's him. Do you know him personally? Bjorn Tigan or Tigan.
I think we can.
What?
We can start.
Yeah. Good morning, everyone. This is the Measurement and Analysis for Protocols Research Group in the IETF. My name is Dave Plonka. This is our co-chair, Mirya Kulevind. And welcome to the meeting, whether you've been here before or you're a new participant. We've got some boilerplate things to go through here. The intellectual property rules in the IETF are similar to the IETF, meaning you're to disclose IPR if you have it in the session here. And the details of it are here if you need to know that. The session is being audio and video recorded. If you are in front of these cameras, you'll be recorded and you'll be on the YouTube videos that are up afterwards. In this group, we go through afterwards and find the checkpoints for each of the sessions, and you can jump to them. So they'll be in the MAPRG wiki afterwards. It's a nice resource for people that may miss some of the sessions. Our privacy and code of conduct here this is something taken seriously in the IETF and the IRTF. If you have any problems with other participants or issues of privacy and conduct, you can contact us. You can contact, if it's with us, you can contact the Ombuds team or someone else in the IETF, and they'll listen and get that addressed. The goals of the IRTF are different than the IETF. We have a slightly looser mission and longer running. So in the IETF in general, we do long running research efforts and sometimes produce RFCs, but we also do a lot of linking with the academic community, academic publishing community. So a lot of the participants here write academic papers and publish in other venues, which is a perfect introduction to MAPRG, because we try to serve as a liaison between those communities for people that do measurement work. So MAPRG would be measurements about IETF protocols or operations to inform them. And that's the thing that Miri and I like to do, is link people up between IETFers and largely the academic community, but it's also the industry that does measurements on internet protocols and their operation and development. So the charter's linked here. We have a mailing list. If you're not on it, that's where you'll see the call in the future. If you want to contribute to MAPRG, get on the mailing list. Obviously, you can also discuss subjects from the meetings there. It's pretty low volume, mostly calls. Today's slides are at this link. The Meet Echo link is there. Please be sure you're signed in if you're in the room to Meet Echo, either the light version on your phone or the full version, because we use that to take attendance. For instance, right now we have 49 people signed in, and that's important so we get right-sized rooms in the future. There's some meeting tips here about, I said the session's being recorded already, but what some of the buttons do and things. And we're going to do this where we're going to ask you to raise your hand, or not raise your hand, rather get in the queue using the buttons there, even if you're in the room, so that it's easier for note takers and scribes to know who you are, and the rest of the participants to find you afterwards if they want to follow up with you. So Miria prepared this list for us from IMC. Curiously, this year, if you're a long-standing participant in MAPRG, you know IMC is one of the top academic conferences for internet measurements, and it changes its schedule. Sometimes it's a little before IETF, sometimes a little after IETF, and when it's after IETF, sometimes we can scoop them and get those authors to come and present here first before they present it at their conference. Sometimes we carry it right afterwards. This time it's happening simultaneously. So IMC is going on today in Madrid. And the interesting thing is we were able to corral some of the co-authors and some of the authors presenting in Madrid to also present here. So you'll have some, the downside is most of the people will be remote because they're participating in IMC, but they will be presenting the same day in Madrid and then again here in this session. So that was really to their credit, but we asked the ridiculous question and they said yes. So these are a set of papers that you might be interested in. Not all of these will be presented here. And I'll go on to the agenda. And what we have here is we've got a balance of about 40 minutes of time, maybe 35 to 40 minutes for questions and comments. Usually we use that up, but there's a little more slack in here than usual. So hopefully we won't have to cut too many people off. I apologize in advance if you're in the queue and we close the queue or we ask you to shut down because we promised some of these people time towards the end of the time slot. So to go approximately like this, the times are for each of the talks are there. The times they start are approximate, but that last presenter is, like it's 5 a.m. or whatever where they are. So we gave them the last slot. I won't go through the details there because you can find them and we'll be introducing them as we go. So the first talk is with the two shorter talks at the front here are heads up talks. Bjorn, you can come up and we'll put his slides up and do those talks first and then move on to the others.
Maybe also very quickly, we did a last minute agenda change because one of our initial speakers got sick, but maybe we can have this as a next session. So if you wonder, there's something missing on the agenda, if you have noticed, that's why.
All right, Bjorn, if you just ask me when you want me to change this next slide, I'll do that.
Will do. All right, thank you. Yeah, hello everyone, my name is Bjorn, I'm from Domos. I'll be presenting some work that we've done with Comcast, measuring network performance with some of their customers. And this is work sponsored by the Comcast Innovation Fund.
Bjorn, can we maybe get a little closer?
Sure, yep. Next slide, please. All right, so in IPPM, we are working on a draft called Quality of Outcome. 5 minutes is not enough time to describe what that is in detail. But very high level, it's a network performance framework designed to reach both to reach 3 different audiences: vendors and operators, applications, and the end user. The main features that we're aiming for is sort of for the vendors and operators, precision, repeatability, and composability, so that things can be broken down by link and we can do root cause analysis and that kind of thing. And then for the applications and the end users, we are interested in communicating like how stable is the network and what types of applications are likely to work well. And then also if the applications do not work well, why are they not working well? So doing root cause analysis and helping pinpoint the root cause of issues. Next slide, please. And I think, yeah, yes, that's good. So this is the method for the study. We sent out emails to existing Comcast customers, offered them a new router, a $200 gift card to be part of the study. We got about 300 respondents, chose 25, shipped them a router. They used it for about a week. And then we sent a new questionnaire and show them a tool that uses this quality of outcome network performance score, and we ask questions about what they think about this score. Next slide, please. So this is the tool that we showed the end users. What this is a timeline of the network quality calculated for a specific type of application. So the end user could choose like video conferencing, gaming, or streaming, and then the time period for which they are shown the data. And then if the user scrolls down here, they can get the score for each of their devices. So it's sort of a quite detailed log of the likely performance of each of their connected devices in their home for specific application types. Next slide, please. So the final questionnaire, we asked questions about, like, does this seem to be correct? And do you like this way of showing network performance data? So next slide, please. And the responses were, in our opinion, surprisingly one-sided on the positive side. We were a bit blown away by the results. People seem to think that this score accurately reflects their experience and that it's more accurate than the bandwidth that they subscribe to or the results of a speed test that they run. Also, encouragingly for the process that we're running here is that people say that it matters a lot that it's a third-party independent public standard and not something that the ISP has come up with themselves. And a lot of people would actually recommend this tool to others. So that's encouraging as well. Next slide, please. And this, I think, is the most encouraging result, which is people seem to think that this score accurately reflects their subjective experience of using the network, which I'm very happy about. And I think that is it makes me hopeful that we can use this as a stepping stone for like redefining a bit what we mean by network quality. Instead of selling bandwidth, ISPs can sell application performance and making sure that networks work well. And that's everything I had time for this talk. But if you're interested in this, if you want to learn more about what we've actually done, how the quality outcome is calculated, how we measure latency and loss and everything else in the networks, please send me an email, like come up and talk to me here. I would, yeah, I'm happy to spend a lot of time discussing this with any of you. So yeah, thank you for your attention.
Thanks, Bjorn. I have a clarifying question. In that slide there, does that mean, is that a respondent count there?
That's right.
So 15 people.
Yes.
And they were happy with it compared to
Yes.
speed tests. You think that might be a biased result based on people that you could reach, or what?
I mean, yes, probably.
Yeah.
I wouldn't expect this to be as one-sided if you actually reach a larger population.
Yeah.
But still, I mean, the trend seems to be positive. That's good.
Great. Thanks for joining us.
Thank you.
All right, we have John up next. John, I'm going to bring up your slides.
Very good. Can you hear me?
Yeah, we can hear you.
Okay, very good. Apologies on it there. We had the kind of network issue that makes the national news in the last week or so. So I'm not really in a position to travel at the moment.
Okay, but thanks for being here. Okay, so you've got 10 minutes and you should have slide control now.
Okay, very good. So basically, this is an experiment that came out of, oops, too fast. It came out of some questions that my supervisor, Dr. David Malone, was asking in a conversation one day. So we said we'd run up an experiment just to see what the answer was. It was around, he was having issues with his ISP, and there was, he had just some queries about DNS and response times and TTLs and how long would records last when they're put out there. So basically we did an experiment, and that's the broad outline of the slides. I'll just keep going. So background is really simple. Put up a DNS server, see how long it takes for things to actually expire with multiple vantage points. And we basically decided to pull down the DNS in various ways. In some ways, we just said we dropped the DNS record itself. Some we dropped the DNS server, and we have a couple of different options to do just to see how it behaved. First scenario was quite simple. Create the record, wait for it to be visible, wait for it to be stable across a large body of resolvers. I'll explain where we got those from, and then basically stop it and basically remove the record, see how long it takes to go away, The second one is just stop named itself, see what happens, shut down the server, or just firewall the DNS port and see that's the 4 scenarios we're broadly looking at, and we've only done 2 so far. There's the setup, quite simple. A Proxmox server up in HENet would be our NREN here in Ireland, up in a data center Park West, and we ran a server on that. So it's completely unencumbered. There is no firewalls. It's very, very high bandwidth. And the glue records from the main master zone point to the test server. So we set it up in RIPEs using Atlas RIPE measurements. So basically, we're getting a view from all over the world, from various parts of the world, as to what they are seeing in our DNS as a response. We set up our SOA record as specified there, 3 hours for refresh, retry in 15 minutes, expired in a week, and basically minimum or negative caching of 1 hour. And the expiry and the week one is interesting. You'll just see why in a short while, because it's created some more questions for us. Methodology is quite simple. Entering the zone file. Once the number of responses stabilizes, remove the entry, roll the seal number forward, reload the zone file, and see what happens. So basically, you're removing the entry from the zone file. And for server fail, it was much simpler. Once the number of responses is constant, once the number of resolvers hits around the 50, which is the number we set for the experiment, shut down bind, and see how long it takes for everything to disappear. So it's quite simple, really. So this is what we have for the first set of experiments, where we just dropped the A record, and as you can see, there's no straight, there's nothing apparent, there's no obvious pattern here, there's no obvious degrading. And what we did is we ran the different experiments starting at different times of day to see was there anything specific to the time of day. And what we did in every entry was we stopped, every time we did the test, we stopped on the hour. So there was always going to be an immediate drop due to the RIPE measurement. It goes plus or minus 10 minutes around the top of the hour when it runs the experiment. So there's no apparent correlation between decay rate and time of day, but that's what we saw. And you're looking at hours there. You can see it's not. It takes surprisingly long time for all the records to disappear. The TTL, the TTL would have been. I'll quickly go back to there. It was all left to the defaults there, so that's what the TTL was. The TTL itself would have been the default as well. I'll actually have to check that specifically for you, but that's a good question. Thanks. So it's the default TTL with the SOA. Okay, I will go and check that to be sure. So that was the first experiment. So there's a couple of questions out of that I'll come to in a minute. The second one was this, which surprised me. So basically, I was on holidays and I left the experiment run initially, and there was only 2 resolvers in the experiment pool kept a TTL of 30 seconds and kept the record alive for over a month, even though the expiry was set to a week, which really, really surprised me. I started it again, a second experiment, and after 2 weeks, I stopped the experiment because it really, or 12 days, as it was still showing the same. So I'm assuming there's a mistake in something I'm doing. So I'm going back to redo it again to check and see what the issue is. I'm going to rerun it again. So I checked as well, the connections to the authoritative server are seeing a connection refused. So basically on the actual resolvers, the experimental resolvers, we're seeing server fail. So I would have expected that the record would have been purged much sooner than that length of time. Yes, so open questions. From the first experiment, one of the things we want to check are the resolvers dropping off at the same rate each run? Are they consistent, or are they not? Is it just purely random? Is there detectable caching of stale results. Well, in the second experiment, it looks like there is, but I'm not sure, is that a mistake on my behalf at running the experiment, or is it something else entirely? And then it's just what other errors are we seeing? We should, basically there is a lot of work to be done still on this, and it's to just quantify what errors are we actually seeing. And my principal concern at the moment is there's a mistake in our setup harness. So have we missed some literature here? There's questions for the audience. We know about RFC 8767, but we haven't seen any measurements relating to it. We'd love to see if there are any. I'd love to be pointed at something regarding it. And so there's plenty of open questions there, and that's pretty much it.
All right, thanks, John. We do have a few minutes to give John feedback. This is a work in progress, so we invite these so that you guys can help them steer what they do next. So if you can either remind them what's going on in the DNS community with that, that'd be great. It looks like Wes is coming up, but well, you're welcome to get in the queue. Like I said, we have a few minutes.
My first, yes.
Yep, go ahead, Wes.
So Wes Hardiker, USC ISI. We've done some experiments with TTL related stuff, and I'd be more than happy to work with you to help you debug your situation. I can sort of spot a couple of potential issues just looking at the setup you described, and
excellent.
Would be happy to help. So, reach out to me if you like. There is some pre-existing work. We actually wrote a paper called Cache Me If You Can that was studying TTLs, as well as a colleague of mine wrote one about what happens in DDoS attacks and things like that with TTLs, where you can't get to the authoritative server any longer. I am blanking on the name of that paper at the moment, unfortunately. But if you write me, I'd be happy to drop you some references.
Thanks, Wes.
All right, anyone else? Okay, thanks. I think that'd be it, John. And you have contact information here. Who do you want them to contact if they're contacting you, your team?
Contact me.
All right.
Yeah, but I just want to say I thank you for coming here. I think this is why we have this forum. So like if people do early work, please come here, and we hope we can help you to connect or getting things running.
Thank you.
Yeah. And sort of on that point, I have done that before with my own publications, and sometimes you have a citation that literally says personal conversation with so-and-so, and it happened at IETF. So it really does help to bolster your ability to make a good argument with your academic work. So, all right, I'm going to stop your slides, John. And we're going to bring up Margarita's slides next. And this is one of those amazing people that volunteered to present from Madrid, I guess 1 hour east of us. All right, Margarita, I have your slides up, and let's see, yeah, I'm going to pass control to you now. So you should have control of the slides, and then you've got 15 minutes.
Cool. Thank you, everyone. I'm excited to tell you today about our work reverse engineering congestion control algorithm behavior. Just for a little bit of context, I'm a PhD student at Carnegie Mellon University and at the University of Lisbon. So as you may be aware, congestion control algorithms, or CCAs for short, affect every internet connection. They define properties such as whether competing applications share bandwidth fairly, how stable bandwidth allocations are, and whether network links are utilized efficiently. And these and other properties of CCAs have long been an active topic of study by the networking community. One important aspect of these research is that for it to happen, for us to check these properties, we need to know the behavior of these CCAs, how they work. And with the rise of new applications in the web, more and more companies are deploying proprietary CCAs. And for these, we don't know how they work, so we can't really validate these properties. Even the known CCAs, they are implemented in code that looks like this. It's thousands of lines of code in some programming language, and the sheer size and complexity of them makes it hard to analyze. Since we can't observe behavior from the implementation, either because it's not available or because it's too complex, we propose to use packet traces. Packet traces are no more than timestamped records of how much data was flying in the network at any given time, and they look a little bit like this one that I'm showing here. And we're not the first ones to think of packet traces as a way to describe the behavior of CCAs. Here I'm showing you some orthogonal line of work to ours, or not orthogonal, but parallel and related, where they use the same kind of packet traces to train a classifier, so that then when they have a new packet trace of a CCA that they don't know what CCA is running, they can use the classifier to have a prediction of which CCA is running. And an important aspect of these kinds of works is that you start by these labeled data set, and then you're able to identify CCAs that were in this data set. If something is new, something you've really never seen before, these kind of work will just tell you that it's unknown. So we wonder, what if a CCA is truly new? Can we say more about it? So the goal of our work, this one that I'm presenting to you, is to generate simple implementations of CCAs from packet traces showing their behavior, with the overarching goal of making the analysis of known CCAs easier and the analysis of unknown CCAs possible. The system I'm telling you about today, the one we built, is called Abagnale, and we use a technique called program synthesis, which we borrowed from the programming languages community to try and reverse engineer congestion control algorithms. And the first important insight that we needed to apply program synthesis to CCAs is that most of the code, I showed you that it looks like this, is actually boilerplate. And what I mean by this is that even though we have different CCAs showing different behaviors, a lot of the code looks the same for all of them, and only a small portion will change from CCA to CCA. This small portion is what we will refer to as event handlers. And these are just small functions that look at what is happening in the network. They look at some signals that signal to us the things that are happening, and they will update the internal state of the CCA. All the rest of the code is boilerplate, and we will just sort of plug that in afterwards. So to reverse engineer congestion control algorithms, we'll focus on synthesizing only these event handlers, which can then be used to build a complete CCA. These handlers are basically functions. They take as input the network signals that I was telling you about. They are just ways for us to know what's going on in the network, and they take as input the previous state of the CCA. In this case, I'm using a congestion window as an example, but it could be any state that the CCA is maintaining. And then they output the new state, the state that is going to be working in the CCA from now on. And then the output of each execution of this handler will be used as input to the next execution. So the behavior of the CCA that we observe in the trace, the number of packets in flight at any given point, is just the result of the successive execution of these handler functions, the thing we're trying to synthesize. So I will quickly explain to you a little bit how Abagnale synthesizes the handlers. And we use a sort of typical architecture in program synthesis, which has an enumeration loop where we look at candidate solutions, and for each one we check, is this the handler we're looking for? And in order to understand the loop, the first thing we need to look into is the DSL. DSL stands for domain specific language, and it's the language in which we will define our handlers. These are typically implemented in C or some programming language, but our DSL is going to be a little bit more constrained than that. It will include congestion signals that can be used as input, anything that shows us what's going on in the network. It will include operators that can be used to combine them, and it will include numerical constants. Then our handlers will just be compositions of these DSL components. I showed you the Reno example. The handler looks like this. It grows the window proportionately to the number of ACT bytes. But you can also see these handlers as just a composition of DSL components. It uses 3 operators and 3 congestion signals to build the handler function. So what we'll be looking at is the space of programs that we can compute or we can build from composing these DSL components. The problem with this is that the more expressive we make our DSL, the larger our search space is going to be. And in fact, it's going to be exponentially larger. So if we were to look at just 6 DSL components, the 6 that I showed you we can use to build Reno, we would only be looking at 100,000 handlers. But if we, for example, add enough to represent something a little bit different like BBR, we would already be looking at 100 million handlers. Abagnale in total supports 13 different kernels CCAs, which requires 25 DSL components, which is then around 60 billion handlers. But actually, it's only 60 billion handlers for small programs of what I'm calling depth 3, which is just a measure of how complex the handler is. Abagnale actually looks at programs of up to depth 7, which means that our search space is already more handlers than there are atoms in the universe. As you can imagine, there's no way we can go over all of these. So our enumeration procedure has to be pretty smart. We start by using a solver-based pruning technique, which is just a logic encoding of certain properties that we want our CCAs to have, our handler functions to have. And this removes from the search space anything that doesn't type check, doesn't unit check, or is somehow equivalent to something that we know we've checked before. And this solver-based pruning, I won't go into detail, even though it's very, very cool. It removes 99.999% of the search space, but it still leaves us hundreds of thousands of handlers to explore. So to explore this still pretty large search space, we apply a divide and conquer approach where we just partition the search space and we parallelize the search. And the challenge here was to find a way to partition such that each part is disjoint and it can still be encoded into the enumerator. So we can still use the solver-based pruning that I was just telling you about. Okay, so when we enumerate candidate functions, the next or the following step in this loop that keeps on going is what I'm here referring to as simulation. And the goal here is for each candidate to check if it's showing the behavior that we want to see. And so we start with the packet trace that I've been showing, the timestamped record of how many bytes are in flight. And for a candidate CCA, the simulation we run is executing it in the same conditions that we can observe the packet trace. So we take the signals from the packet trace and we execute the handler that we are evaluating. By doing this, we get a second trace, a second timestamp record of how many bytes are in the network, and then we can compare these two traces. So when we are collecting our trace, the methodology we're using actually is subject to some measurement errors, some collection errors that we can't really get around. So even if we were executing an exact handler that would be exactly the same, we would never be able to match the collected trace because it's noisy. So instead, we look at the distance between the collected trace and the synthesized trace, and we compare different candidates to see one that is close enough. So we just run this loop. We explore as much of the space as we can within any time constraints that we have until we find a handler that has the minimum distance between the collected trace and the synthesized trace. You can see in our paper, we evaluate Abagnale, and we struggled a little bit to find a good way to evaluate the handlers that Abagnale was giving to us. And the way we end up doing is by having a handwritten version of the handler that was fine-tuned by a domain expert. So we have the handler that we believe the CCA is doing, and we have the handler that Abagnale is telling us the CCA is doing. And we run this experiment in 13 well-known Linux kernel CCAs, as well as 7 unknown CCAs implemented by students as part of a class. Our results, which again you can find in the paper, they find semantically correct handlers for everything that is Reno-like, everything that grows the window with the proportion of the number of act bytes. For other CCAs, such as Vegas and BBR, we find something that I'll call proximate, semantically proximate. And I won't go over the whole thing. Please find it in the paper. But I will show you what I mean by that in the case of BBR. So as you might know, BBR, its traces look very characteristic. They do these spikes. So every periodic amount of time, they spike the number of bytes in the network to check if there is more bandwidth available than it's using at any given time. So we were able to write an expression. This was written by a domain expert by us to describe BBR's behavior, where looking at the paper and the source code, we can see that these spikes happen every 8 RTTs. So we write that expression, we define the baseline of what the bytes in flight is in every other time, and then every 8 RTTs we spike. Abagnale was able to find a similar handler in that the base base rate at which it keeps the bytes is correct, and it also figures out that sometimes it needs to spike. However, it's not able to figure out the periodic what's the trigger that makes the spikes happen. So this is what the kind of result we call semantically proximate. The base behavior of the CCA is there. There are some occasions in where it doesn't match exactly. Okay, so I hope you enjoyed. I showed you Abagnale that we use to output simple implementations of CCAs based on packet traces. I'm happy to take any questions.
All right, thanks, Margarita. You have us right on time. Anyone want to join the queue? Any questions or comments?
I see a question in the chat. Should I answer this one or?
Yeah, go ahead.
So the question is, what is the distance metric here? Between the traces, I assume this part where I showed you that we compare different traces using a distance metric. We actually tested many or a few different metrics, and we ended up settling ours on something called dynamic time warping. You can find the results of our different experiments in the paper. And the interesting thing about the dynamic time warping metric is that when in cases such as this, where the spikes are happening, but they're a little bit shifted on the x-axis, dynamic time warping will actually compensate for that, and we will not penalize these kind of only in the x-axis distance.
Perfect. Stuart, you can go ahead.
I'm Stuart Cheshire from Apple. Not a question, just wanted to thank you. I think this is really great work. After our community has worked on the internet for 30, 40 years, getting congestion control right remains a really hard problem. Thank you for doing this. If you haven't already planned it, it would be great to show this work to the congestion control working groups. Unfortunately, ICCRG is meeting right now, so that's a conflict. But we have the congestion control research group, and we also have the congestion control working group, the IETF and the IRTF groups, and I think this would be interesting for both of those.
Okay, thank you.
Yeah, also, I mean, talking about measurements for a second, are you out there hunting to find new congestion controls in the wild? Or would you be interested in getting traces from people in order to find or detect new congestion controls? What's your plan?
Are you asking Stuart or Margaret?
No, I'm asking my reader, but Stuart, you can also say something if you want.
Yeah, we would be very interested in that. We tried some experiments. They had a big problem, and we don't really include them in the paper, which was that if we don't know what the congestion control algorithm is, if we really don't have the source code, there's really no way of validating the results that we get. And also, if we don't have close access to the server that is running them, it's a little bit hard to make the measurement of the trace, to collect the trace. And with bigger noise, the error of our algorithm goes up, and it's a little bit harder to get results. But yes, we would very much like to have access to traces of CCAs that we don't know what they're doing, so we could see what we can find.
Yeah, maybe put something on our mailing list as well. And probably the mailing list is also a good resource for figuring out if you really can't detect something, you need some ground truth to figure out the right people to talk to. So I recommend that.
Okay, thank you.
Thanks so much for making the extra effort to join us today.
Of course.
Bye-bye.
Enjoy, IMC.
Thank you.
All right, so we have Huyan up next. And Huyan, if you can turn on your video and your audio, that'd be great. And I'll bring your slides up.
Hi, can you guys hear me?
We can. Very good.
Okay, great.
And so these are your slides, yes. And
Yeah.
I will transfer control to you, so you should be able to control them yourself.
Okay,
And
perfect.
you've got 15 minutes. Go ahead.
Okay, thank you. Hi, my name is Puyan Potritharani. I'm presenting a talk on CAA, CT, and DANE technologies that are used to mitigate and avoid certificate misissuances on the web PKI. This work is with my colleagues Rafael, Teresa, Thomas, and Matthias from Technical University of Dresden, as well as HAW Hamburg. And we're going to talk about security on the web, most specifically on the X509 certificates that are used for authentication. So you have your server, you have your client, your TLS connection, you exchange the certificate, the client can authenticate if you are who you're claiming to be. To get a certificate, you go to a certification authority, you subscribe to that CA. The CA is going to validate if everything is okay within the certificate. It's going to sign it, create a certificate. The client is going to validate that certificate if the certificate is issued by some CA that it deems trustworthy, meaning that it has the certificate of the public key of that CA in its so-called trust store. The certificates that we have on the web has at least a domain name inside. So this is a very basic thing that CAs do. They validate if the person who is applying for a certificate actually controls the domain name or controls the web server that the domain name is pointing to through an IP address, and then issues that certificate. We are going to focus on the CAs because they have a lot of control on what's happening here. And we're asking if what can go wrong if we can trust CAs. And the reason being is if you look at the trust store from Mozilla, you're going to find about 55 different organizations from around the world which have their root certificates inside, and there are about 666 intermediate CAs. And you have to imagine these are the companies that can certify domain names that you own, and you might not even heard of them. It's a very critical security operation that we have going on, and a lot can go wrong. The CA can get compromised. Um, you can have unauthorized certificates due to some problems that you might have with your infrastructure operators. The CA might go bunkers. They might just misbehave as Symantec did a couple of years ago. And you might have CAs that are there actually for government purposes of interception and surveillance. So a lot can go wrong. You cannot trust CAs with everything on the internet, because in most of the cases they are also not constrained in what they can certify. So they can certify every domain name on the internet. And if they do so, if they misbehave, if we have misissued certificates, it's very hard to detect that. So we need to give some control to name owners when it comes to their own namespace. And we have a lot of, not a lot of, but a couple of solutions to that, starting with the Certification Authority Authorization, the CAA. The idea is that the name owner can denote which CA is allowed to certify names from my namespace. I have an example here from a German bank called DKB. The first policy, the first line says, if any of the following policies are violated, inform me. Drop me a line at hostmaster@dkb.de. The second line says, only DigiCert is allowed to issue fully qualified domain names for my namespace, and no CA is allowed to issue wildcard certificates. These policies are controlled by the time that a CA wants to issue a certificate, and before that and after that, they are actually irrelevant. So it comes only to the point of issuance. Then we have DANE, DNS-based authentication of named entities. The idea here is that the name owner can describe what certificate is to be expected at an endpoint. We have an example here from internet.nl. It says that if you're communicating at my HTTPS endpoint, port 443 over TCP, there are 4 certificates that are relevant, that are authorized. They define here actually CA certificates, not lead certificates, and they describe those certificates by the hash of the public key. And what the client do is over the TLS, they fetch the certificate and they see if the hash of the public key of the certificate that they got from the server matches any of the hashes on the DNS. Dane relies on DNSSEC for the security, and Dane records, the TLSA records, are validated each time that a client wants to validate a certificate. And finally, we have the certificate transparency. The idea here is that every CA just publishes their issued certificates on public certificate transparency logs, and anyone can monitor those certificates, those logs, and find out any problems. Browser vendors such as Chrome and Safari actually require a certificate to be logged in a CT log before it gets accepted. So in practice, every CA actually logged their certificate. So now we have these 3 approaches, and we are interested to know how they are used. For that, we take the Tranco top list. We take the full list. It comprises of more than 4 million domain names. We resolve the domain names, follow redirects. We collect all relevant DNS records. We collect certificates from TLS connections as well as CT logs. And we analyze that. And the results, first, each aspect on its own, starting with CT logs. As I said earlier, every CA actually logged their certificate because they don't want their certificate to be rejected in browser. So everything is logged. It's logged in prominent logs are from Google, from Cloudflare, and Digisurf. And among the CAs, it's a known fact. Let's Encrypt is on the top. Automated, free of cost. Everyone is using it. One thing that is interesting, especially later when we talk about the efficacy of these approaches, is that the technologies are concentrated in the hands of a few. If you look at Google, for example, they have their own PKI, they have their own CT logs that they run, they have their own browser, so they control a lot of aspects of the web PKI. Moving on to CAA, we see about 5% of the domain names use CAA at all, and most of them actually authenticate the server, the certificate that is deployed on the server. We see one interesting special class of classification that we introduce is implicit matches. These are the cases where the CAA policy does not constrain issuance, but there is a policy existing for a domain name. And according to the CAA semantics, if you don't constrain issuance, but you have a policy, it means that everyone is allowed to issue certificates for you, which is a slippery slope because in cases of typos, as we have here, this is a real example that we have here, the name owner wanted to constrain issuance only to Let's Encrypt, but it spelled issue with 3 S's. So in practice, it's interpreted as everyone is allowed to publish from me. So implicit matches are one case of interesting thing that can be misconfigurations that remain unknown to the name owners. We also see mismatches. So the CAA policies do not match the certificate that we observe. This does not necessarily mean that the CA has done something wrong, but since there's a time discrepancy between our measurements and the time that the CA actually queried the DNS records, it might be that the DNS records have been changed or have been dropped and so on and so forth. And you can see on the diagram below that the older the certificate is by the time of measurement, the higher the chances are that we classify CAA mismatches. So this is, in most of the cases, measurement artifact that we have here, but there are also cases that we observe CA misbehaviors. Most of the cases, the name owners just concentrate on the issue tag. So if you only give a CAA policy using the issue tag, you cover both FQDN and wildcard certificates. None of the top CAs that we observe actually support policy violations. So if there are illegitimate applications that don't match the CAA policies, the name owner is not going to get informed, although it is in the specifications. We see that CAA records are defined at different hierarchy level of the DNS, mostly at the domain level, at the direct domain level, in 9% at the parent. So if you have example.com and you're looking for CAA records for it might be also defined at example.com. The specification allows defining policies anywhere in the DNS hierarchy up to the root. We see that there are identifiers for certification authorities that are not unique. So different CAs use the same identifier or accept the same identifier. The example is here that everyone who runs on the Sectico infrastructure uses Sectico identifiers. For example, if you go to Zero SSL, it used to be an Austrian company that uses the Sectico infrastructure. You might have never heard of Sectico, but the documentation says enter Sectico, and by doing so, you actually open up issuance for a lot of CAs that you might not know. The takeaway is that configuring CAA is not that simple, despite of the simplicity that the specification suggests. If you want to correctly validate, it's a time-critical manner. So you have to have the same snapshot of DNS as the issuer had at the time of issuance. None of the CAs, as mentioned, support violation reporting. And since you can define CAA records at any level of the hierarchy, even zones, parent zones that do not have any control of your zone can define CAA policies for your namespace if you don't do that yourself. Dane is barely used. The dog is a Great Dane. So if you're asking why there's a dog, that's a Great Dane. We see only 1% of the domain names actually use Dane, and 1 out of every 5 of them actually don't have DNSSEC. So the whole purpose of Dane is defeated here. We see that about 10% of the TLSA records reference CA certificates, 87% end entities, and the rest both. Depending on what type of certificate you reference using your TLSA records, it has an impact on your TLSA maintenance frequency. We see, interestingly enough, that only 70% of the Dane records actually authenticate deployed certificates. So we have cases where 30% there's a mismatch. And we also see invalid certificates. This is a valid scenario in Dane because Dane also allows you to use self-signed certificate and everything that might be considered as invalid within the context of web PKI. So Dane is rarely deployed and in part misconfigured. My understanding is that if browsers were to support Dane, we were to see a much higher penetration of Dane, as we see that among the within the email ecosystem. If you look at, for example, Microsoft, who reluctantly use DNSSEC for their domain names, they use Dane for all of their inbound and outbound exchange communication. So now that we have each one on its own, let's move to look at a combination. We were interested to see if you have a domain name with CAA policies, are there other certificates out there that are not deployed? And if so, how they match to the actual deployed, to the CAA policies for that domain name. We found for 191 domain names with CAA policies, we find 766,000 certificates on CT logs, and for 2% we see a mismatch. So the certificate that we find has a different matching state than the certificate that is deployed. We try to somehow visualize that. On the left-hand side, you see the matching state of the deployed certificate on the server. On the right-hand side, the matching state of the certificate that we found on CT logs. So we have cases where the deployed certificate matches CA policies, and the CT log certificate does not, and vice versa. The reasons are different. As I said, there's a time discrepancy. So not every mismatch is actually a CA fault. It might be a measurement artifact. And we also have cases where people have moved on from one certificate, one CA to another, and so have changed, renewed or rolled over their certificates, and the old certificate still exists on the CT log. We go the same way for Dane in combination with CT. And one thing that we make use of CT here is for that 30% of TLSA records that don't match the deployed certificates, we want to find out, are there certificates that they actually authenticate? We looked at the CT log and we found for every TLSA record, we find a certificate in CT logs that is actually being authenticated. We divide that into two groups: expired certificates and certificates which are now valid. The expired certificates show you that there was a time that those TLSA records actually were pointing to a good valid deployed certificate, which is not the case anymore, and someone has forgot to remove or update those TLSA records. We see certificates which have been expired for more than a year and still exist there. And on the other hand, we see valid certificates which are not being deployed. The reasons are unknown, but it might be maybe you have different access points, different servers with different certificates. I don't know, maybe over CDN, but you only authenticate one certificate and not all of the certificates at your endpoint. We also go the same way as we did for the CAs, and we look at every domain name that has a TLSA records. We look if we can find certificates on CT log and how they match with the DANE records. I'm not going to get into details. Maybe we come back to this, but we find interesting scenarios that you have, for example, a backup certificate as Cloudflare does. So Cloudflare applies for multiple certificates for a domain name, deploys only one, replaces it if something goes wrong, if your key is compromised. And we see that people only reference to the actually deployed certificates, and everything that is not deployed remains out. And so if anything goes wrong, your DANE configuration are going to be wrong. So again, TLS records are poorly maintained, and if you don't take into the account of actually the deployment settings that you have, I don't know, CDN or whatnot, your DANE configuration is gonna have is not gonna have the security assurance that you're going for. Then we looked at DANE and CAA. I'm just gonna skim through it. One thing that is interesting, okay, the top part, you see the red bar. The red bar is showing that the DANE configuration is incorrect. The green bar, everything is good. One thing that we take away from here is, okay, TLSA misconfigurations are undetected. If you have CAA, you have configured it correctly, but you have misconfigured TLSA, it means that you know how your name server works, but you don't know how to configure your TLSA. And we see if someone manages to have perfectly correct DANE configuration, the chances are higher that their CAA, that they use CAA are also more often. So let's sum it up. I'm at the end. So securing Web PKI, at least when it comes to certificate misissuances, is ignored by far. When we are using DNS-based security protocols such as CAA, DANE, or even domain validation, we need to secure DNS, but we don't. We have only 5% DNSSEC penetration. CAA semantic is ambiguous. I'm going to get into that during the question session. Validating CAA is not that easy. We have to have the same snapshot as CA, and we don't. CAA does not prevent misissuances if your CA does not respect CAs. If it's broken, it's compromised, whatnot. DANE is rarely used, although it can completely replace the CAA semantics, besides the policy violation, which is not used by anyone. Maintaining DANE is complicated. You have to synchronize your deployed certificates with your DNS records. Name owners are left in the dark. If they misconfigure, if they have typos or whatnot, they are not going to get informed. And all in all, it seems that users are unaware of the whole complexity. We communicated with a lot of name owners during our measurement, and we found out like copy paste configurations that were incorrect, but the users were unaware and whatnot. So I'm just going to finish it up. I see some movements in the chat. So if you're using DNS for anything security related, we need DNSSEC. So that's my point of view. I'm looking forward to hear from Mr. Houston that I look up to. We see that the CAA specification appeals to ideas like unique identifiers, but in practice, in deployment, it's not being respected, so it weakens the security. We need some kind of authoritative mapping, like YANA, that says, okay, if you use this identifier for your CAA, then these CAs with these fingerprints are allowed to issue certificates. we can use CT logs to decrease the time discrepancy that I mentioned earlier. We actually have a paper going on that. Dane can enhance, it can actually replace. If we move away, leave out the policy violation, then Dane can completely replace CAA. And if we have someone who can tell in real time what those configurations mean to the name owners, we're going to have a much secure landscape all in all. So that's it. If you have questions, critique, or you want to work with us on these topics, I'm really glad to hear from you now or per email. Thank you.
Yeah, thank you. You do have questions, so Wes is first in the queue.
Wes Hardiker, USC ISI. Thanks for the work. It's always good to see more analysis like this. I will say you are right that the web browser ecosystem had no interest in Dane, which is why people don't check the Dane records for the web system. That being said, Victor Duchovny and I do a large-scale scanning project for mail-related things, and there are 4.2 million perfectly valid Dane records used on the mail side, validating domains. One of the things that we have noticed in that effort is that, like you say, a lot of people are using Let's Encrypt. Well, Let's Encrypt actually rotates your key on a regular basis. And so you have to keep your Dane record in synchronization with your rotating key, or tell Let's Encrypt to stop rotating the key, which both possibilities. You're right, there is also not a great notification mechanism. Victor's well-organized system actually auto emails people when their Dane records are broken so that they can go out and fix them. Microsoft, as you said, announced just last week that they're now doing inbound Dane protection for all of the domains they host. So it's heavily used in that ecosystem, but not at all in the web system.
Thank you. Yeah.
Hi, Greg Choules, ISC. Do you think there's anything we can do to make it easier for users and more obvious to get over the headache of how to work out how to create CAA and Dane records in the first place, so that it gives them less incentive to just not bother doing it because it's too difficult?
Yeah, thank you. My personal opinion is that if at least the very first step is to have some kind of standardized way, like the IANA does for DNSSEC parameters. You go there, it says, if you do this, it means that. So if you say, if you want sectical with this fingerprint, if you want to allow them to use CAA, then you have to put this identifier. That would be the first step. I don't think that everyone is aware of what the actual meaning of each identifier is. We see a lot of copy paste, and we see even infrastructure operators have errors in their documentation. So that's one thing that can be do. In my opinion, we have a paper going on. It's not published yet. We point out a number of deficiencies, if you would say, of the specification of CAA on its own. So you can have different semantics using different syntaxes on CAA. And so it's not really crystal clear. The example that I gave, that if someone has a typo, they're not going to be aware of it. The CA is going to say, okay, it's perfectly clear, and everyone would go their way without detecting that problem. So I think it should be at least some kind of feedback from the CA. Okay, your policies mean this. Is this correct or not? Or your parent zone defines policy for your domain name. Is this something that you're okay with? Or do you want to define your own? I think these are the things that remain undetected by the name owners.
Yeah, I think feedback is necessary, because otherwise people just won't know whether they've got it right or wrong.
Yeah, exactly. Yes.
Thank you.
Thank you.
Okay, thanks a lot. Oh, we have Jeff.
Yeah, hi. Interesting talk. It certainly parallels a lot of work and a lot of frustration I think all of us have had for many years over this. The problem is that DNSSEC is just finding it really hard. And certainly in real-time applications, Nobody wants to pay the validation penalty. Walking backwards up, doing all the unraveling of signatures just takes too long. There was a really good approach done around 10 years ago called chain extensions, where in theory, what you do is you bundle up all the answers because you know what the questions are going to be, and you send back all the validation data in one hit. That's great, except that it's a bloody great packet and it doesn't fit in UDP and nobody wants to go there. And so we're in this frustrating area that it would be really good if we could trust what we learned from the DNS. And DNSSEC can give you that. It's just that no one wants to actually re-engineer the DNS to carry awfully big payloads just for that application. There is a bunch of other issues around the fact that keys confuse everybody, all of the time. Everyone gets them wrong all of the time. And so that combination has proved fatal for Dane. It's proved fatal for CAA. We live with a thoroughly compromised TLS system that could be better if it just had a little bit of help from Dane, or we actually took the entire thing over and popped it into Dane. But we then need to make DNSSEC work in the DNS. And at that point, the task becomes beyond what we've proved capable of doing over the last 20 years. Would that it were different? Thanks.
Thank you. I'm really happy for your comments. I've been following you in the past couple of years. I watched a video from you from 12 years ago, and I'm in that situation where you were very excited about DNSSEC. So I'm you like in 12 years ago. But I think a lot has changed. You're right about like those huge packages that we have there, and so on and so forth. The point is that you have DNS over HTTP, you have DNS over TLS, you have everything that doesn't have those UDP luggage that you're talking about. So I'm more hopeful that we can manage to go that way, to have DNSSEC working without all the obstacles that you mentioned. My 2 cents. Yeah.
The mainstream of the DNS is over UDP. It just is. You know, all that DNS
So,
over
we have
everything
to-
else is a
sorry for
minuscule
interrupting
proportion.
you.
Anyway, yes, I'll stop.
Yeah, so we have to take this discussion offline. There's also comments in the chat just to relay this here a little bit about measurements, that maybe the latency impact isn't that big, but if somebody wants to bring more measurement data about this, we're happy to take this. Thank you for this comprehensive study, and we move on to the next talk.
Thank you.
Thanks, Pion. So we have Johanna Ulrich up next. Johanna, you can turn on your video and audio, please, and I'll share slide control with
Hi,
you.
do you hear me already?
We hear you, yeah.
And
So you should have the slide control now.
now you all. Yeah, looks good. Thank you. Okay. Thank you very much. We're also an IMC talk, and in our case, it's not only the same day, but also I just got a photo from my colleagues that they just finished their talk. So, you know, it's really strict timing. We start, so we switch protocols. We now switch to IPv6, and I'm not telling you anything new that you cannot fully scan the address space there. And from that, we started our work, because what we wanted to do is, or the basic idea of our work is, in IPv4, you basically look for the positive answers. And as these answers are very, very scarce, you should also investigate all the other responses that you get. So even negative answers can tell you something about the remote network. And this is exactly what we are doing in this work. We look at ICMP and the messages and what they reveal about the remote networks. I think I can do the detour into ICMP very short. Most of you know it from pinging, so you can ping an IP and get a response, hopefully, and see for diagnosis purposes. And there are also other message types like destination unreachable, which has 7 subcodes, which provide you more in-depth information on the cause why you couldn't reach the IP address that you actually probed. And then again, there's a third message type that's again more known. It's the time exceeded. So when you end up in the routing loop, and the packet finally is filtered. So in the past, so these messages have already been used, but primarily to collect additional addresses and to get very large data sets of IPv6 addresses. And what we do, we don't only extract the addresses, but we analyze the type of the messages and also other parameters to get more information about the remote network. And basically, we have two insights. The one is we can infer on the activity state of the remote network. The idea here is if you come back to reconnaissance, you will only find active hosts in active networks. So you can guide your scanning efforts, for example, towards those active networks, because those that are inactive, it doesn't make sense to have any further to spend any further effort on that. And the second is about routers. So we can use the rate limits of routers to infer the type or their version. But first, and in both cases, we started with a controlled environment to reduce complexity. So we had a virtual environment to test certain scenarios, and afterwards we verified our hypothesis on the internet, and then we went to IPv6 flight measurements. So the first step was the router lab. So we had here a bunch of virtual router setups, and there we had 6 different scenarios that we implemented according. So we looked at the RFC and tried to reestablish the scenario in which certain error message are triggered, and looked whether that was consistent with what was in the RFC. And the response or the result might not be that much surprising for those that are longer in the standardizations. Let's say the standard was adhered in many cases, but not in all. So for example, what we see here in the first row is that we saw no route in different scenarios. So, and also if we look that are scenarios that both are related to inactive networks and to active networks. And what we did when we had these scenarios, that we classified the error type, whether it was related with active networks or inactive. And many of them had to be considered ambiguous because they occurred in 2 versions. Because here, for example, this microtic thing reacted different than all the others. What we also had is address unreachable. Address unreachable should usually be returned if the IP address cannot be resolved into a MAC address. But this means that there is a router listening to this network. But for one router, we even found that it's returned in case of a null route. So we even would have in the first round to classify this address type as ambiguous. But in the end, we could still make a subtle differentiation, because this resolution from IP address to MAC addresses usually has a timeout, which is 3 seconds or even longer. So we could just measure the round trip time and say, okay, if it's longer than a second, it's an active network, because then it tried to resolve the address. And if it's shorter, it's more this null route thingy. So then from the control network to verification on the internet, and there our problem was, where do we get labeled addresses? I mean, there are hit lists out there of active addresses, but we need are actually addresses that are unassigned addresses in active networks, and then addresses that are for sure in inactive networks. And so we did a trick so we used the active addresses from the hit lists and randomized more and more of the final bits of the addresses, and looked for the returned messages. And as soon as we had a change, we said, okay, the one before the change, that are the one for the active networks, and the others are then from from outside of the network. This is the short exclusion. Obviously, there are some fine-tuning aspect on that as well, but that's the rough idea. So with that, we have labeled data sets, and we could measure them. And what we found is that, so first of all, maybe go to the right picture with the round trip times in first place. We see that we also have with the address unreachable these delays, most of them 3 seconds, sometimes some a bit longer also on the internet, and not only in our lab. And what we also see that when we're measuring with ICMP, so we send echo requests or TCP, we can label active networks with an accuracy of more than 90%. Classifying inactive networks is not as good, but still it provides you a hint. So, and then third step out into the wild. This is just an example measurement. What we did is that we took the PGP prefixes of length 48 that are announced in PGP and sent a request to each 64 in that. And on the right, there's impression how it looks like. Yeah, we have found some active and some inactive networks. But what you have to consider, and this is maybe the largest drawback of this work, there are still some networks who do not reply to ICMP at all, with ICMP messages at all, and obviously you cannot measure them. So that's maybe the largest drawback of our measurement. So, and now I already said we can say something about the activity status of the network, and we can also say something about the routers. The idea is here to use the rate limiting behavior of routers. According to the DRC, there should be a rate limiting algorithm, so the router should be limited to a certain quantity of ICMP error message that it sends, that it originates, and they are usually token bucket algorithms. So they have certain points that they can use to spend on sending ICMP messages. And if this bucket is empty, they have to wait for the next refill, and then they can send again. So what you see is then this typical pattern here. And what we see when comparing many different routers in the lab again, that these limitations are different. So at the top we see the Cisco and Juniper devices and so on. And what we also see is that all the Linux-based appliances, they behave non-surprisingly quite similar. But what we also saw some other differences, like some have a rate limit per source address and other have a combined rate limit for all of them. So there are subtle differences, and that is then what we want to exploit for getting the vendor or the version of the remote router. The Linux-based versions, they have a very specific feature, let's call it feature, yeah. Their rate limit developed over time, also because there was a bug in the code. So there was code inside Linux that didn't work properly, and it took some years to come to a conclusion that there was an error in code, which is why we have early version where there is a static source-based token bucket algorithm, and that is, so per IP address there's a rate limit. This later then becomes a global rate limit, and in a third case this rate limit then becomes adapted and is depending on the prefix size of the destination. And in the end, there is, again, a randomization of the bucket size. Long story short, there are changes over time, and we also use them as a fingerprint. So again, we had to go from our lab to the internet, and there we used a data set of SMP3 vendor labels that was presented in 2021 and compared our measured routers that were in these data sets with our technique to look for whether there was an overlap, and we see that it fits quite nicely. So for this, the vertical bars are what we saw in our lab, and we see, for example, that the Microtic routers overlap with what we've seen for the Linux-based version, as well as, for example, Huawei and Cisco. Obviously, it's not 100% fit because the SNMP3 data set also involved types of routers that we haven't had in our router lab. So we also used it to extend our fingerprints. Yeah, and after we have somehow proven or shown that our method works, we measured 1.4 million IPv6 capable routers. We extracted their addresses from a previous topology measurement, so a trace routing measurement, and so we knew they were routers and measured them with our technology, our method. And what we were able to, because we had this trace routing measurement before, we could differentiate routers that we observed on multiple paths from those that were only seen on one path, and with the intention to separate more routers that are more to the core of the internet from those that are more on the edge. And this is very well reflected in the results, because the one that are more to the core, the typical vendors appear, like Huawei and Cisco and so on, while the one that are more towards the edge, we see only or predominantly Linux-based devices. And what's most interesting is that more than 80% run a Linux version that has reached end of life, either at the beginning of this year or even at the beginning of 2023. So most of them are outdated, actually. So that's it from my side. So we use ISMP error messages on the one hand to classify the activity status of remote networks. As I said at the beginning, as a first step towards reconnaissance. And with that, I think I paved the way for the next talk already. And the second is that we can classify routers. And obviously, it makes also sense to combine these two information, because as I have shown at the beginning, some router types behave in a way that's not coherent with the standard, and you might find out the type of the router in a first step to then classify or have more information to classify the ISMP error message types and to infer back on the activity status of the network. So, and that's from my side. And I have to admit that I forgot to watch on the clock, so I hope I didn't overdo it.
No,
Yes,
you're
I'm sorry.
right.
Okay.
No, you hit it exactly right on time.
Okay, perfect.
We have Lorenzo in the queue. Let's take one question really quick, and we're just down to half an hour left in the session for 2 15-minute talks, so we're going to go quick.
Lorenzo, yeah, I was curious what you see. Maybe it's in the 38% of stuff that just doesn't respond at all. You know, these mobile devices that have /64s directly connected to them, what do? Do they sort of not respond? Because they have their 64 generally directly connected to the interface.
Yeah, I cannot say that precisely. That's a good hint, because this is why we did this step from the lab to the verification measurements, let's put it, because we thought that there might be so much out there on the internet that we haven't considered because we simply don't know. Yeah. So that we had to test whether our method is working. So it seems like either they work, they respond in a way that's standard, yeah, or they do not reply at all. But I don't have any. I cannot say the precise answer yet. No, but it would be worth to.
There's not routers.
Because they are not routers, yeah.
What they should do is, I missed it. I also had, oh, I see you.
There is also maybe a short interruption here. There is also because this destination, while time exceeded, for example, is a must, you have to return it. All these destination unreachable, they are a should, so they don't have to be returned. So, but sorry.
You
again.
had a lot of like /96, like 97 or greater prefix sizes. What do you think that is? Is it 127s or? So there was a
again.
There was a lot of Linux at the edge, Linux with like long prefix length at between 97 and 128.
Okay.
Yeah.
No, that's so we have some measurements that these are very rare. And I said maybe I skipped the detail because it is very an in-depth detail that the rate limit of the Linux versions is dependent on the prefix size, and so we can classify it either as a version, this Linux version, or very small networks. And so our conclusion is these networks are very rare, so it's more likely that these are this Linux version.
I
Yeah?
misunderstood. Thank you.
Okay.
Right. Thanks so much, Johanna, for joining us, and thanks Lorenzo for those. We're going to switch to Grant's presentation, and Grant, you can do your video and audio.
Yes, hello.
I'm going to pass control to you, so you should have that now, and you got 15 minutes.
Great. Okay, so I'm going to be talking about seeds of scanning. I'm Grant Williams, by the way. Seeds of scanning, understanding the effects of datasets, methods, and metrics on IPv6 address discovery. This is also something we're presenting at IMC this year. So overall, in this book, we evaluate 8 different IPv6 scanning target generation algorithms across multiple different datasets, ports, protocols, and metrics. And then we come up with a list of best practices for TGA use. So internet scanning and for TGA use in internet scanning. So internet scanning has been around for a while. I think many of us use it on a daily basis, or at least familiar with it. It involves connecting to devices open on the internet on a certain port or protocol. The state of the art for this, for IPv4 is ZMAP, which brute forces the whole IPv4 space. But for IPv scanning, it's a lot more difficult because of the address space. You can't do this brute force approach anymore. And so we have to come up with other ways to discover addresses, one of which is some of the ICMP error message work that we just heard. Another approach that's commonly used is target generation algorithms, or TGAs. So how a TGA works is you take in a bucket of seeds. So these are IPv6 addresses that you can get from all sorts of different sources, from DNS to trace routes. We're going to talk about those sources in a little bit. And what you want out is a list of IP addresses that weren't in those seeds that are very likely responsive. And so then you can go scan those and use them for measurement, do whatever you want to do with them. And hopefully find a lot more new interesting devices. So how TGAs do this is they take in these seeds and they split them out into sort of patterns, or they extract patterns from these seeds, and then they guess these output IP addresses based on those patterns. Now, how they do this pattern generation is magic. We're going to think of it as a black box. It's magic. We're not going to go into details of how they do that. Technically, it's there's tree-based algorithms, there's different machine learning algorithms, and many, many more. But for our analysis today, we're going to talk about these as just black boxes. Okay, so there's been a number of different TGAs that have been proposed over the last 10 years. And typically, one of the main metrics that's used here for evaluation is hit rate, with the percentage of the guessed addresses that are responsive. Now, you would expect that over time, as improvements are made to TGA algorithms, new TGA algorithms are proposed, and with the increase in adoption of IPv6, that the reported hit rates over time in a lot of these works would go up. And so taking a look at these reported hit rates, we get entropy IP with 43%, all the way going through 6gen, 6tree, det, 6hit, 6graph, 6scan, and 6sense, which was all Usenix work from this year as well, which isn't totally a TGA, but it's close enough for all discussion here. Now you can probably tell from this, this doesn't go up and to the right as one would expect. So what's going on here? Well, what's going on is that each of these papers, each of these prior TGAs use a different evaluation methodology, different seed input data sets, and even some of them use different definitions of what hit rate might even mean. So there's very little consistency here. And the evaluation, we really need that consistency in order to be able to kind of evaluate these TGAs going forward, and especially consistency in these input data sets. When every prior work is using maybe a different construction of an input data set, it makes it really hard to compare, how good are all of these TGAs, and if you want to use them for measurement, what should you use? So our goal is to really define some of these best practices for running these TGAs, specifically around defining the seed dataset design. And there's been some prior work in this target acquired from 2023, but this looked primarily at TGAs on variations of the IPv6 hit list, and it had limited analysis, some but limited, of multiple ports, protocols, metrics, and preprocessing. So we really wanted to focus on that preprocessing, especially, and how we set up these seed data sets when we put them into the TGAs to sort of optimize what we're able to discover on the internet. So our method for this, we evaluate 8 different TGAs, 6int, 6tree, 6hit, 6scan, 6graph, 6gen, det, and entropy IP, over 21 different seed dataset variations, different kinds of preprocessing, different seed dataset sources. We're going to talk about all of those in a little bit. We scan 4 different ports and protocols, ICMP, TCP/80, TCP/443, and UDP/53. And we generate for each of all these combinations, we're generating 50 million different addresses. So we evaluate these generated addresses on 3 different metrics. We look at hits, the number of these discovered addresses. We look at the autonomous systems with hits, so the network diversity that we're able to find. And then alias hits. And I should note that the hits here that I mentioned earlier are de-aliased hits. And we're going to talk about what aliasing is in a little bit, if you're not familiar with it. But essentially, we want to decrease the number of aliases that we're finding in aliased hits. Okay, so in order to come up with these 21 different seed dataset variations and do all of these experiments on preprocessing, we need to have some seeds to start with that we can start to preprocess and that we can start to look at different variations of. And so we collect our seed datasets from 12 different dataset sources, but these are, roughly speaking, split into 4 different high-level types. So the first dataset type that we're looking at is domain datasets. So this is where you get a list of domains from CT logs or Rapid7 or domain top lists, and you run quad A lookups on them, and then you get back IPv6 addresses. The second is traceroute address discovery. So that's where, if you run a traceroute on a random address, you're going to, even though there might not be anything there, you'll likely get back the IP addresses of routers along that path. And so there's various different data sets that have done that, Scamper through CADA and Wipe Atlas, and so we got data from them on some of these router addresses. And that ties a little bit back to I think some of the prior talk we just heard as well. So the third data set that we're looking at was looking at prior TGAs, prior data sets of addresses that were generated. So specifically, we took a data set of addresses generated by Address Miner, which is a TGA based on det, that's more focused on long-term generation, det being one of the ones that we're evaluating here. And then the third approach that we took was we took data from the IPv6 hit list. So this is a combination of all these different approaches, and it has some good historical data. It doesn't overlap fully with any of these approaches, though, that we took. So total, we found 118.7 million addresses. Among those, only 10.9 million were responsive on one of our different, on at least one of our 4 ports and protocols. Virtually all of those were responsive on ICMP. And then the responsive, and this was across 23,000 responsive ASs. Okay, so we have our data set, we have a methodology. Now kind of going into the experiments that we're going to do, that we're going to talk about. We explored how some of this data set cleaning and preprocessing impacted these TGA results. Then we went into combining results across multiple generators and how that could help us find more things. And then we looked into source dataset specific results that we could find. So we're going to talk about each of those. So for the seed dataset cleaning, pre-processing, one of the main things that we started by focusing on, we looked at 3 different kinds of seed dataset pre-processing. So the first was removing aliases. Now, aliases are prefixes in the IPv6 address space where the entire prefix is responsive. And this would be trillions and trillions of addresses. And typically, this is only a single device or a handful of devices responding on this prefix, but it can trick TGAs into thinking that there's all these interesting new devices that are responding. And so we typically want to filter those out, or at least we don't want them in those our final results, because they're just not really as useful for. They can tend to bias a lot of our results in the end. And so we wanted to look at filtering out these aliases beforehand, filtering them out from the seeds, and then seeing how that affected the TGA generation. We used a few different approaches to de-aliasing, which I refer you to the paper to look more about. We don't have time to talk about them in depth here. The second approach we took was looking at removing inactive addresses. So we have, so recall that there was 118 million total addresses, but only about 11 million of those were responsive. Now, some of those are de-aliased responsive, so some of those 118 million were aliased, but a lot of them were also just inactive. They didn't respond to anything. So what happens if we sort of filter out all of those inactive addresses? Can we target more towards the addresses that we're more interested in, or like the TGAs are more likely to find addresses around, and the regions that they're more likely to find addresses around? So last, we have port-specific data sets. So let's say you're scanning TCP/80. Do you want to include active responsive data from other ports and protocols? And this is specifically important here with respect to ICMP, because virtually all of these addresses in the responsive set are active on ICMP. So this is really also looking at, should you be including addresses that might have something there, but they might not necessarily have something on the port and
I think we lost your audio.
Did something change on your side?
No, we can't hear you, Grant, but you can. Why don't you try maybe leaving the MAPRG or leaving the Meet Echo and joining again? Grant, can you hear me?
Or maybe you can try at least to rejoin the audio.
Rejoin the audio. You mean Grant can?
Grant
Yeah,
can.
Grant, maybe drop your video and audio and come back.
Yeah, I disconnected his audio, so if you request audio again, maybe we can try that. But maybe he can't hear us at all. No,
Okay, I just got him on the chat. So.
Okay, is this better?
Yeah, you're back.
Wonderful. I'm sorry about that. I don't know what happened. Okay. So yeah. So going on to actual results here. So for alias removal, we end up this is very, very good for increasing hits, increasing ASs, and it takes down aliases to virtually nothing across TGAs. Similarly, for inactive removal, we're getting there's no aliases at this point once we remove aliases, but we also do target more towards interesting regions. For port-specific data sets, this is where metrics start to really matter, because honing down to port-specific data sets does kind of cut out more network diversity. We don't find as much network diversity, but we do find more hits across some TGAs, so it's kind of a trade-off. So overall recommendations here: filtering aliases is important, filtering unresponsive addresses is important, and then filtering these port-specific responsiveness is important depending on what you want to, depending on your metric. So taking a look quickly at these prior TGA results, you'll notice that when we have this new standardized data set and a standardized sort of evaluation methodology, this curve looks a lot, makes a lot more sense. There's some dips, for instance, but a lot of these TGAs in this dip are related to tree-based generators. So some of this could just be variation in performance there. And then the intuitive observer might recall that 6sense had 15.4%, or had a 10% hit rate before, and now it has 15.4. That's just differences in evaluation methodology and changes over time. So are we done? Is this it? 6sense seems to be the best performing TGA out of these. Do we just take that if we want to do an internet measurement, and we take this data set that we've come up with? Is that it? Is that everything we do? Well, unfortunately not. It's not quite as easy as that. So turns out not all TGAs are finding the same addresses.
Hey, Grant, can I interrupt you a sec?
Yes.
We're really near the end of the time. If you could help us out by maybe jumping to a summary or something. You're at.
Sure. Yeah. Actually, this is my. I'll skip to the next section after this.
All right.
Just jump right to the summary.
Thank you.
So yeah, broadly, just looking at overlap with TGAs, tend to find that those things don't overlap exactly. So I'm gonna skip over looking at seed data set specific, but there's more information than that in the paper. Broad overview there is just looking at seed data set specific data sets, or source specific seed data sets can tend to find more address diversity. So broadly, best practices here for running TGAs. One, you're going to want to de-alias the seed data sets before using TGAs. More approaches for that are in the paper. You're going to want to filter unresponsive IPs. You want to filter by protocol responsiveness, depending on what metric you want to optimize for. Using multiple TGAs in combination does tend to find different addresses because many of them find addresses in different ways. And then we didn't have time to talk about it here, but look at the paper for more details. But running TGAs on sort of multiple smaller data sets can tend to find more network diversity. And so really designing your seed data set towards also if you want to find certain ASs is possibly a good idea. So broad high-level takeaway, seed addresses have very big effect here on the output of TGAs. This pre-processing is very important, and just so that we're able to use these TGAs going forward for internet measurement, it's very important we kind of have this standardized evaluation going forward. So researchers are able to kind of know what TGAs to use, how TGAs perform. So yes, I don't know if we have time for questions. If we do, happy to take them, but if not, we can also take them offline.
Yeah, Grant, I'll apologize for that technical glitch. Don't know what it was, but I think for your colleague who has the last talk slot,
sure,
we're just going to go to there. So reach out to Grant if you have a question or comment. Thanks so much. And Tianru, I'm going to bring your slides up. And you can get yourself with the video and audio set up. Can you say something?
This is the wrong slide.
Oh, sorry.
Can you hear me?
Oh, let me get here. Scroll down. IoT bricks. Sorry.
Yeah.
All right.
Right.
Welcome. You're ready to go. You're going to take us to the end of the meeting.
I don't have the control of the slide.
Oh, you're right. There you go.
Let me try. Okay. Awesome. Okay. So our paper is also about IPv6, but it's on consumer IoT devices. So my name is Thierry. Like our paper is also accepted at MC 2024 this year, and it's a collaboration with Dr. Daniel Duvat, Professor David Chalfnis. Okay, let's get started. So we all know that IPv6 adoption has been slow over years due to many reasons. That said, there's a considerable amount of traffic that is over IPv6 right now. So this data is from Google. I think like many of us are already familiar with this. So we also know that most commonly used operating systems support IPv6 natively, which means most of you like personal devices are running these IPv6 ready operating systems. So unless you are a Nintendo Switch user, which run an OS that doesn't support IPv6. But we can fairly say that most general purpose consumer computing and networking devices in a typical home network setup that support IPv6 right now. So however, like in recent years, smart home IoT devices become more and more popular. So the household penetration rate is over 50% in the US, 25% in the Europe, and 18% worldwide. So IPv6 can solve like the addressing problem for IoT devices and provide improved remote access. But we don't know like if popular smart home IoT devices on the market actually support IPv6 and how do they use it. So in this paper, we have two rows. First, are consumer IoT devices ready for IPv6? If not, why? To what extent are IPv6 features supported? And which IP version do IoT devices prefer in a dual-stack network? And the second row is what are the privacy and security implications of using IPv6 on IoT devices? So to answer our question, we first set up a test bed with 93 IP-based devices, IP-based IoT devices from 7 categories and 45 manufacturers. So we designed 6 experiments to test their functionality on their different network setups. 1 IPv4 only as baseline, 3 IPv6 only network, and 2 dual-stack network setups. So all the configurations are commonly used settings for residential network. So please check out our paper for more details. So to test if they are functional in certain network condition, we design a functionality test. So we consider a device is functional if their primary function is working. So depending on the like device category, so it can be like totally device state or streaming YouTube or TV. So what did we find from our experiments? So we have 93 devices. Only 8 of them are considered functional in IPv6 only networks. So the answer to this question is like obviously no, most of them not ready. But despite not functional properly, like many of them do show some level of IPv6 support. So we found 59 of them have IPv6 traffic. 51 of them assigned themselves at least one IPv6 address. 22 of them query DNS in IPv6, and 90 of them get a valid IPv6 DNS response and send data to IPv6 internet destination. So many of them have some level of IPv6 support. So there are like 34 devices with no support at all. 8 have traffic but no addresses. 29 have address but no DNS. 3 have DNS but no data. And 11 have like everything but still not functional. So why is this? So the reason is that there are multiple factors involved in ensuring the functionality in IPv6. So if any of one of the necessary component is not configured properly, the device won't operate. So I will use some example here to explain it further. So first, like there are 11 devices supporting all IPv6 feature, but remain non-functional in IPv6 network. So this is because of their reliance on IPv4 only domains. So although like these devices talk to some IPv6 destinations, so these domains are not essential for their functionalities. So the domains that are essential for their functionalities are still over IPv4 only. So why are they IPv4 only? Because of the failure to provide or use IPv6 DNS coded entries. So DNS is definitely a huge component here to support IPv6, and I have more example about DNS here. So first, their clients are not fully ready. In IPv6 only networks, 90 devices send a only DNS request for certain domains, which means that although they can send DNS in IPv6, these devices are not configured to support cloud queries properly. And in dual-stack networks, there are 33 devices send cloud requests, but only in IPv4 for certain domains, which means that despite supporting cloud record, which is good, they don't use IPv6 or IPv6 DNS resolvers for this record. So how about the server side? We did the active cloud query experiments for all their destination domains, and we found 73% of their destination from the 8 functional devices are cloud available. But among the 85 of the non-functional devices, only 31% of the destination are cloud available. So this is definitely another important indicator of IPv6 support for IoT devices. So the last example here is that there are 29 devices assigned IPv6 address, but not sent any DNS. So this is because like they don't have the global IPv6 address. So they use local IPv6 addresses because some smart home standards, such as HomeKit or Matter, mandate them to use it. But they just don't configure internet IPv6. So after talking about all this example of not working in IPv6, how about the functional devices? So here are all the functional devices. So it's very clear that first, manufacturer has a significant impact on IPv6 support. So these eight devices are from these 4 manufacturers, but similar devices from other manufacturers may not have full IPv6 support. For example, like this Fire TV clearly says that IPv6 may limit their functionality. So for many major manufacturers, we did not find any of their devices support IPv6 like the 4 manufacturers on the left side. So certainly, device category also matters. Smart TVs, smart speakers, those devices running more running on more sophisticated software that updates regularly, often like have better IPv6 support, compared to the home automation, smart cameras, or smart appliance. So this means their OS or their software stack has a significant impact. So of these 8 devices use operating systems that natively support IPv6. Well, other devices like the home automation devices, they have limited resources on device, as they may not want to run a OS or software that support IPv6. They may see IPv6 as an unnecessary component for now, because most of the users are still in IPv4 or at least still stacked network. So what about their preference of these 2 IP protocols? So we found that in dual stack network, 2.8% of the domains use IPv4 only, despite receiving valid coded records, as there are 11% of domains from IPv6 only experiments fully switch to IPv4 when IPv4 becomes available. So although RFC recommends prioritizing IPv6 over v4, it's not the case for many smart home IoT devices. So what about privacy and security? So first, some background on IPv6 addressing. So when this IPv6 addressing was defined, it used a method that used the device MAC address as the interface ID to form like IPv6 address. So the MAC address is like stable, unique, and traceable. So they can be used and are actually actively being used as tracing ID. So the latest RFC suggests you that you should not use it. There are research from like both industry and academia about the privacy and security issues. So how many of our devices still use it? So 8 of them still use it for DNS and 5 of them use it for data communication with 27 domains. So we classify this destination domain based on their owners. We found one of them is a third-party analytics server, which has some privacy concern here. So we disclose our finding to the manufacturer of these 8 devices, and all of them acknowledge our disclosure and indicate there are like potential mitigation in future release. So what we learned. So first, obviously, smart home is not ready for IPv6. That's our title, IoT bridge over v6. So why is this? Our speculation is that this is due to the lack of incentives. So the device vendor, network providers, network administrators, like all must develop and maintain IPv6 support for software, DNS, library, OS. But do they have enough incentives? No. IPv4 still meets the connectivity needs for IoT devices, and there might be interoperability issues, security and privacy considerations on supporting IPv6. So the cost of supporting IPv6 might be even higher than the not supporting IPv6 for some IoT manufacturers. So all of the factors made them hesitate to support IPv6. So to encourage the transition, we still need joint efforts from all stakeholders. So the policymakers and standard bodies can also create incentives for consumer IoT devices, IoT vendors to improve their IPv6 support. And as I mentioned before, there's a new IPv6 standard called Matter that has been adopted by most of the IoT vendors right now. Although it's a local network standard that mandates them to communicate over IPv6 within the home network, not to the internet, but we believe that it's a good first step. How much time do I have right now? Okay. So this is the end of this paper, but we also have a research overview of our research over several years. So we are a research group from Northeastern University. We have several public data sets and software on IoT measurements. So just if you are interested, feel free to reach out to us or go to our website for more details. Okay, thank you so much. I'm happy to take any questions.
Yeah, thank you so much. And especially thank you for getting up so early for us. We are at the time, but if somebody wants to ask a quick question, we can take it. And we have one person in the, yeah, Lorenzo.
Lorenzo Colletti, just wanted to say that for I think especially for Matter, IPv6, off-link or IPv6 connectivity is actually fairly difficult because it's, especially for Thread, it's on like a stub network. And so it needs things like sort of NAT64 or DHCPD to work. And that's sort of even harder. I think we don't have a great way necessarily of doing NAT64 in the home, in home networks yet, right? I mean, I think you know, a lot of stuff just isn't implemented. So
Yeah, I totally agree. Like, yeah, it's a first step, but it's definitely not the solution for IoT, like on IPv6.
Okay, thank you. That means we're at the end of the session. I hope you enjoyed the session, even though we had mostly remote speakers. We will try to get more people in person, but it's actually nice to have remote support next time. But at least we had Dave here in person, so that's great. And then I also want to say thank you to Alan, who was taking notes for us today.
Thanks much. Enjoy the rest of the week. Looking forward to seeing you.
Thank you.
Thank you. That worked out well. A little more balanced. I think you.